Um, okay, yeah, and getting into some of these filters here. Earlier we were talking about the bilinear, bicubic, which bilinear is 2 by 2, bicubic's 4 by 4 matrix. Here we're using a 3 by 3 matrix. So it's not the most complicated, it's not the most simple way. Just a medium there. Of course, like I said earlier, type of matrix depends on how much computational resources you have. But just getting into this matrix, this low pass one right here, this one's pretty intuitive, I think. So the center matrix is the current pixel you're looking at essentially, and you can say that this is making it so that from a human's perspective there is that blurring because you're just averaging all these pixel values together, right? And then for this Laplacian, right, this is a high pass filter, so you are highlighting the center, but you are giving a negative weight to the edges of that pixel. So that's going to obviously create those. It's going to highlight the high frequency points because if there's a point that's very different from its neighbors, it's going to be enhanced, and its neighbors are going to be um, decreased with that negative weight there. You can see we also have the vertical and horizontal filtering, um, which is going to highlight the or high pass vertical and high pass horizontal, which is going to highlight the vertical and horizontal edges. Um, and we also have a, or I guess we can see all the filtering happening here in this for loop. So we have, the grainy image, then we have the regular image, and we're just looping through and doing each one of those 9 functions. And we're using the image filter MATLAB function here to perform that. Um, and then getting into part B, we can see here we have a histogram of both of the images. So this really gives us a good um, representation of the pixel layout in terms of right, the color is a result of the bit values. So I don't necessarily know what it is here. Maybe um, zero is pure black. Oh, sorry, yeah, I do know because it says right there. Zero is pure black, and then 256 is pure white, and of course that means that we're doing uh, 8 bits because we have 2 to the 8th power is 256 levels. And you can see, yeah, just visually by looking at it, you can see there's a lot of black, of course, which you can see with this big spike here. And there's also a lot of white as well with that spike. Um, yeah, and then that's this section here. Then in this section, we are doing a Fourier transform. Of course, a Fourier transform, very useful thing in signal processing, is we're looking at the frequency spectrum of some sort of time domain function, right? So if we take the Fourier transform of a sine signal, for example, that's one frequency, so it's just going to be a delta Dirac function of whatever frequency it's at. Um, and any signal we take a Fourier transform, the result of that Fourier transform is just going to show us, okay, where is the intensity in the frequencies of this signal. But in the images case, it looks a little different. So we can see between the regular and the grainy the differences here. So the center of this image is low frequency, and as you're getting farther away, that's high frequency signals. And you can really see the difference in the grainy and the regular image here because, the Fourier transform really stops around here. You don't have too many. Of course you do, but not too many high frequency points. And then this one you can see just, I mean, this just looks like white noise almost, which, white noise is essentially just equal quantities of every frequency. So yeah, it doesn't really look like there's, I mean, yeah, you have some more higher intensity at low frequency, but once you get a little out of there, it seems like a pretty similar level of high frequency signals. And that was just done using the fast Fourier transform function. And again, we just looped through those images and just performed the fast Fourier transform native MATLAB function.